Hello everyone. So in this video we'll solve this problem. We have a butt joint as shown below, we have it here, is connected with 3/4 inch diameter bolts. It is to carry a tensile dead load of 50 kips and live load of 100 kips. Using Fy is equal to 36 kSi and Fu is equal to 58 kSi, is the joint's tensile strength adequate to carry the load? Use LRFD. Now before I proceed with the solution, first of all, this problem is actually the sample problem in your module 2. Although in the module 2 it is already presented there the solution, I would like to discuss it here because reading and actually listening to someone that's explaining are two different things. You might learn something from someone who is solving than just reading them by yourself. And most probably some of you might not actually try and solve the example. And if you just read it and not try and solve it, well, the learning might not be that much. So I'll try and solve this in this video so to give you an idea on how to solve this problem, the flow of the solution. Okay, so let's try and solve solution. Before I proceed with the solution, few clarification. This sign, the double line above a number, denotes inches. Okay, so what this means is 3/4 inches. Okay, this figure also denotes diameter. Okay, this is diameter. In some books and in some authors, they do not write the word diameter. Instead, they write this figure. Okay, so don't be confused. This simply means diameter. So we have here 3/4 inches diameter bolts, meaning the bolt has a diameter of 3/4 inches. Next is we have kips. Kips simply means kilo pound, okay, or 1,000 pounds. That is what is meant by one kip. One kip is 1,000 pounds, or in other words, 1,000 kips is 100,000 pounds. We also have KSI. Okay? KSI is that is kips per inch squared. So KSI is actually kips per inch squared. And we know LRFD is the load and resistance factor design. So don't get confused. Okay. Now with those discussed, let's proceed to the example. Solution. As you have read in your module 2, you have step 1. We need to determine which member or which steel member needs to be analyzed. We have here the main members in the middle and the cover plates at the outside. They have different thickness. The thickness of the main member is 1/2 inch. The thickness of the cover plates is 5/16 inches. Now at first, 1/2 is actually greater than 5/16. Now if we go at it here, I know that 1/2 is actually 0.5, while 5/16 that is 0.31. Okay. So obviously 0.31 is smaller than 0.5. So you would probably say we should analyze the cover plates because it is smaller in thickness. But note that the cover plates cover both the top and the bottom part. Now what does this mean? Imagine that this ball pen and its cap, the ball pen and its cap are the two members that need to be joined. Okay, they need to be joined like that. While the calculator is the cover plates, so it's like that. Okay, the setup is something like that. Now note that if the member is the one that will break, you can simply remove the member itself. Okay, but if the cover plates, no, you cannot have one cover plate failing and the other cover plate will not fail. So what happens is the cover plate is actually connected with each other through a process of a bolt, no, in this problem. So when one cover plate fails, the other will also fail. So the cover plates act as one. No? So for a long story short, both cover plate will act as one. And since we have an upper and a lower cover plate, no, they will act as one. So their thickness will be added together. So we have here 5 plus 16 plus 5 over 16. We have here 0.6. And so therefore, the thickness for the cover plates, the total thickness is 0.6. While the thickness of the main member at the center is only 0.5. And since 0.5 is smaller than 0.6, then we will use, no? We will use the thickness is equal to 1/2 inch. So we will use the main member, or we will analyze the main member, which is a thickness of 1/2 inches. We proceed to step 2. Step 2 is now determining the shear lag factor U. The shear lag factor U. And since our main member is actually a top view, side view, our main member is actually a flat. We can consider it as a plate. So for plates, the shear lag factor is 1. That is for bolts and rivets. For plates, shear lag factor is 1. You can check your module 2 for a copy. We proceed to step 3. Okay. Step 3, looking at the placement of the bolts or the rivets, it is not a diamond. No, diamond. The diamond is something like this. The diamond will have smaller value, uniformly increasing or decreasing number of bolts or rivets. Well, this part, it's not uniformly increasing or decreasing. It is also not it is also not it is not in array, no? So it's not diamond, it's not in array, but it is in staggered, because if you notice, there's no bolt here and there's one over here. So it's in a staggered formation. Okay? It's not a straight or a diamond setup, but it is in the staggered arrangement. Staggered arrangement. And since we have a staggered arrangement, we will be using this equation. AN is equal to T. Okay? We have W minus N times DH plus NO times S squared over 4G. Okay? Where T is the thickness of the member, W is the width of the member, N is the number of holes that will be hit in the path, D is the diameter of the hole, the NO is the number of slanted distances, while S is the pitch, while G is the gauge. Okay? So before we can start solving for AN, we need to solve or determine the path no, for our AN. Okay, so let's blow up. Okay, so over here. Okay, so we have it here, the location of the bolts and rivets. or bolts or rivets. Now, how do we determine the path? Now, in step 3, we actually need the smallest value of AN. Smallest value of AN. Smallest value. Now, note that we can create any path that we like, but the smallest value will come from when we will start the path at the top rivet and we will go downwards, and we will only limit ourselves in two rows of bolts or rivet. Okay, by the way, if you look at here, okay, this one, okay, this vertical line here, this is what we call a row of rivet. This is another row, another row, another row. This is what we call rows of rivets. So the critical or the smallest AN will only come out or will only be obtained if we limit our analysis in just two rows of rivet. Meaning our path will only travel within two rows of rivet. Okay. So let's start creating our path. The first path will start, as I've said before, the critical will be when it starts at the top, then it will move downward. You have the first option. You can go here to the left, you can go to the right, or you can go straight downwards. If we go straight downwards, okay, this will be our first path. The second path would be start at the top, then we go to the left, and then we go downwards. That is our straight path. We also have start here, we go to the right. If we go downwards, that path will actually be just the same with the second path. So no need to write that down. So instead, we can try start here at the top. As I've said, we'll only limit ourselves to two rows of rivets. So start here, going to the left. Instead of going down, we can choose to go to the right. No? We can actually write that here. So start at the top, we go to the left. Instead of going down, we go to the right. And then we have the option of going down. That will now be our outside, start up, left, right, downward. That is our third path. The fourth path, we can try going down to the left, we go to the right. Instead of going down, we go to the left again. So we can have this path. Okay, left, right. Instead of going down, we'll go to the left. And we go here. Fourth path. Okay. So I repeat. The smallest value of AN will only come out if you will start your path at the top and move downwards. And you will only limit yourselves within two rows of bolts or rivets. Because you can actually create different paths depending on what you like. For example, I want to create a path. Start at the top, and then we go to the horizontally to the right, and then we go to the right here downwards, and then to the left, and then I want to go to the top again, and then downward, then top, and then go. Okay, so notice you can actually create any path you like, but I repeat, we only need the smallest value of AN. And the smallest value of AN will only come out if you start at the top and you move your way downward. You will not move horizontally. You will not move upward. Instead, you will just move downward. You have the option to go left or right as long as it is still going downward. Okay? And you will only limit yourselves up to two rows of rivet. Meaning, if I start here, go to the right, and then go to the right again, and then go to the right again, and then down. You're actually moving now 1, 2, 3, 4. You are now within 4 rows of rivet. Now the 4 rows of rivet, most probably it will not give you the smallest value of AN because you are now within 4 rows of rivet. So try and limit your path within just 2 rows of rivet. Now the question is, are these the only possible path? The answer is yes. So what if I do this one? Start at the top, okay? Then I go to the right, then go to the right, left, then we go down. Now if you notice, this path is just the same with the third path. It will still give you the same value or answer. So what if I do this path? Let's see. What if this path, this 1, 2, 3, okay? What if this path? I start here, top, then I go down. I will not go down, instead I will go to the right and then go down. Now this path actually is just the same with the second path. Now if you look closely, the second path is in this form. This is just the inverted shape. It's just the same. It will still give you the same answer. So these four paths are actually your four possible path, which will probably give you the smallest value of an. Okay. Now you can see in your module 2 the complete solution for solving each of these paths. Okay. Or I can just write it here, no? For this would be path 1. Okay. We would get an. The thickness is, it does not change, it is 0.5 or 1/2 inch. This is 0.5. The width from the figure, this is 12 inches. No? So this is, all are in inches. Minus 12. The n is the number of holes that we hit the path. For path 1, we hit 1 and 2. So 2 holes. 2 holes. The diameter of the hole. The diameter of the hole is the diameter of the bolt plus 1/8. So 3/4. What is 3/4? Plus 1/8 inch. So both are in inch. Okay, 3/4 plus 1/8 inch. No? You have it here. 7/8. No? So we can have it here 7. Or what's this? 0.875. So we have it here 0.875. So I repeat, the diameter of the hole is the diameter of the bolt plus 1/8 inch. And then we have plus NO is the number of slanted distances. For path 1, there are no slanting distances. So this is actually 0. S is the pitch distance. Okay. If you look at here, the pitch is the distance parallel with the load direction. The load direction, if you notice, it is horizontal. Therefore, a distance parallel to the load direction, that is your pitch. So we have it here 2.5. Now note that 2.5 is actually the distance between the outer row to the center row. Okay. So our pitch is actually between just these two closest rows, which is half. So our pitch is half of 2.5, which is 1.25 inches. Okay. While the gauge, this is actually this one. No, I forgot to draw it here. The dimension, this is actually 3 inches. No? This is also 3 inches, and this is also 3 inches. So we have our gauge distance is 3 inches. Okay. Gauge is also a distance perpendicular to the load. So if you notice, this is the gauge distance, and this is the load direction. So they are perpendicular. So the pitch is 1.25 squared all over 4 times the 3. Okay. Let's try and compute in the calculator. 0.5 times 12 minus 2. Let's have it here. Okay. 0.5 times 12 minus 2 times 0.875. Plus, obviously, this entire area will be 0 because of that one. So we have 5.125. Okay. For path 1, no, for this setup. By the way, for your module 2, probably the numbering of the path might not be the same. Okay. In here, the path 1 is this one. Okay. I repeat, in your module 2, the path numbering might be different. Like this could be path 1, 2, 3, and 4. But in this problem that we're solving right now, I labeled this one as path 1. So we have 5.125. Okay, so 5.125. So AN is now 5.125 inches squared, no? Because that's the area. For path 2, we have it AN, still the same, 0.5, still the same, 12. Path 2, how many holes did we hit? 1, 2, 3. Okay, 1, 2, 3. So 3 holes. So this 3 same hole diameter plus how many slanted distances? You only have one slanted distance. So 1 times 1.25 squared over 4 times 3. Okay, solving it here. So this is 0.5 minus times 12 minus, this is now 3. 3 plus 1 times 1.25 squared all over 4 times 3. And we have our answer is 4.75. So AN is 4.75 inches squared. For path 3, AN still the same 0.5, still the same 12, still the, we have, how many holes did we hit for path 3? 1, 2, 3. 3 holes for path 3. 3 holes, the diameter of the hole is 0.875 plus how many slanted distances? 1 and 2. 2 slanted distances. So 2 slanted distances. So 2 times 1.25 squared, 4 times same gauge. We now have the AN value. 0.5. Oh, 0.5. Okay, from here. 0.5. 12. This is 3.875. So we now change the 2 slanted distances. Our answer is 4.81 or 4.82. 4.82 inches squared. Let's now proceed to path 4. Path 4, AN, still same thickness 0.5, same width 12. How many holes did we hit for path 4? 1, 2, 3, 4. 4 holes times same diameter of the hole plus how many slanted distances? 1, 2, 3. 3 slanted distances. 3 times 1.25 squared all over 4 times same gauge distance. Let's try and solve. Okay, let's see. There. 0.5 times 12 times 4 holes. Okay, 4. And then how many slanted distances? 3 slanted distances. That's the answer. 4.45. Okay, 4.45 inch squared. So let's compare now which one gives the smaller AN. So the smaller AN or the smallest AN is this one, 4.45. So we now have our value for AN. Let's proceed to step 4. Step 4. Step 4 involves AE, solving for AE. A is simply AN times du. AN times du. We previously obtained u, which is equal to 1. So 4.45 times 1 still be 4.45 inch squared. That is your AE, or the effective area. Next is we need to solve the step 5. We need to solve the rupture strength, no? Which is equivalent to phi Pn or 0.75 Fu times AE. Okay. This equation, of course, is using LRFD. By the way, we have a different equation for ASD. But since our problem asked us to use LRFD, we will use the LRFD equation. So we have 0.75 FUAE. FU, that is actually your 58 KSI, your rupture strength or rupture stress or your rupture stress. So we have 0.75 FUAE. So our rupture strength will now be RS is equal to 0.75 times FU is 58 times AE is 4.45. Okay, so you have RS will now be 0.75 times 58 times 4.45, equivalent to 193. 193.575. What's the unit? Okay, so we have, this is KSI or kips per square inch. This is square inch, so cancel this square inch. We're only left with kips. We have not the rupture strength. Step 6. Step 6. We need the yield strength YS, which is phi Pn, or which is equal to 0.9 times Fy times the gross area. Okay, the gross area, or Fy times the gross area. Now we know we already have the value for Fy. It is given in the problem. You have it here. Fy is 36 KSI. So we have it here. Ys is equal to 0.9 times Fy, which is 36 KSI. Now what is the area gross? Okay, what is this area gross? Area gross is actually your total cross-sectional area of your member to be analyzed. So if it has a thickness of 1/2, it has a width of 12 inches, therefore its gross area is simply thickness times its width. So it's thickness times its width. So the gross area is thickness of 12 inches. I mean the width of 12 inches times your half or 1/2 thickness. So this is now your gross area. So we multiply all of that, we'll get our yield strength. So we have it here, 0.9 times 36 times 12 times 0.5. 194.4. 194.4, and that is kips. We now proceed to step 7. Step 7. We need to compare. Comparing our values, we have the rupture strength is 193 while the yield strength is 194. The smaller value will be our design strength. The smaller value is 193. Therefore, for step 7, okay, over here. Step 7, our design strength. Therefore, our design strength is 193.575 kips. This is actually the value for the rupture strength since it is smaller. So this is now our design strength. Proceeding to step 8. Step 8. We need our ultimate load, PU. Okay? Ultimate load, PU. Now, ultimate load PU can be obtained by using the formula 1.2 dead load plus 1.6 live load. Of course, this formula is for LRFD, or the load resistance factor design, and this is based off NSCP 2015. Okay, I repeat, LFRD formula for NSCP 2015. So 1.2, the dead load is, from our problem, the dead load is 50 kips. So 50 kips. Plus 1.6, the live load is 100 kips. So we have, let's start, 1.2 times 50 plus 1.6 times 100, 220. 220 kips. Finally, we have step 9, the last step. We compare now our design strength with the, we now compare the design strength with our ultimate load. Now, if you notice, the ultimate load is bigger. The ultimate load is bigger than our design strength. This means that the joint's tensile strength is not adequate. No? The joint's tensile strength is not adequate to carry the load. Okay? Any number that exceeds 193.575 will make our joint fail. Okay, so this is now the limit of our joint's tensile strength. And since 220, which is the maximum load that the dead load and live load will apply to our joint, 220 kips, is greater than 183.575. Therefore, the joint is not adequate to carry the load. That is all. Thank you.